Right, so now let's do a section about the proof by mathematical induction. This proof is the most uh, iconic method, that is one of the most important proof method that is introduced in the IB Math HL level. You're going to see this type of question the most often if the IB exam decides to put a proof question. The proof by mathematical induction is always the go-to one. So we need to be really fluent in this language. So, what is this proof by mathematical induction about? The idea of the proof by mathematical induction is can be represented using a domino. So imagine that we have a domino listed out in order, and if you've ever played with domino, the point is that you knock one of them over, and then it hits the subsequent terms, and it um, knocks everything out all at once. Right. So we're using that principle here. We're suggesting that we have a domino set up, and we're going to actively knock the first one off, and then assume that it knocks everything out all at once. However, we need to make sure that this domino is working in this system. So how do I check that? Well, so we're going to knock off the first one, and then we're going to make sure that for a given n equals k, so for the kth term, we're going to make sure that the kth term does knock the k plus 1 term over. So by showing that the first one is true, and by showing that kth one proves the k plus 1 term, then we can say that we have proven every single scenario for all n values. Okay, so um, let's try these two example problems here. By the way, when to use the proof by mathematical induction? Well, in most cases, it'll tell you to use proof by mathematical induction. But if you're doing some random questions about proofs and you don't know which one to use, if you see the phrase like for all n, for these values of n, when you see those cases, that's a good sign to use a mathematical induction. Okay, because we want to show that the proposition is true for all n values in the domain. Okay, so let's try the first example question here. So our task is to prove that 4 to the power of n plus 2 is divisible by 3 for all n positive integer n values. So let's try. So what do I need to do? Well, I need to show that this proposition is true for n equals 1. So we call that a base case. The base case is for to show that the proposition is true for n equals 1. So that's pretty easy. Let's plug in the value. 4 to the power of n plus 2 will become 4 to the power of 1 plus 2, which is 6. Is 6 divisible by 3? Well, indeed. 6 is divisible by 3. So therefore, we know that and for n equals 1, the proposition is true. So now we know that it works for the first case. Now the next case is to show that the kth one shows that the k plus 1 term will be true. So we're going to say assume that for n equals k, the proposition is true. So in this case, what we're saying is that assume that 4 to the power of k plus 2 is divisible by 3. Okay, so that's my assumption. We're not going to prove this right away, but we're going to assume that this is true. Okay, now I think we can mathematically write this statement that 4 to the power of k plus 2 is divisible by 3. I think one way to show that is that 4 to the power of k plus 2 can be represented as 3m, where m is an integer. Right? If m is an integer, then 4 to the power of k plus 2 will be 3 times m, so that's a multiple of 3, so therefore it is divisible by 3 for sure. Okay, so let's use this fact to prove that for n equals k plus 1, the proposition is true. So we want to prove that the 4 to the power of k plus 1 plus 2 is divisible by 3. So once again, I think we can try to represent this as a mathematical statement. So our goal will be to find the integer value such that the 4 to the power of k plus 1 plus 2 is equal to 3n, for example. Right? And important thing to note when we're using the proof by mathematical induction is that we need to actively use the assumption that we just had. So how will that be achievable? Let's think about it. So we know that 4 to the power of k plus 2 is equal to 3m. I think we can write such that the 4 to the power of k is equal to 3m minus 2. So I'm going to use this expression inside the 4 to the power of k plus 1 plus 2. Let's think about it. I think that 4 to the power of k plus 1 can be represented as 4 to the power of k times 4 to the power of 1, right, using the laws of exponents. And I know that 4 to the power of k can be represented as 3m minus 2. Now let's proceed further. So I got the expression 12m minus 6. And then I know that this can be factored by 3, like this. So what did I get? I know that I can represent 4 to the power of k plus 1 plus 2 as 3 times 4m minus 2. And we can say that because m is an integer, we also know that 4m minus 2 is an integer. Therefore, 3 times 4m minus 2 is divisible by 3, which we can also say then. Therefore, 4 to the power of k plus 1 plus 2 is also divisible by 3. So, do you see what we did here? We prove that the base case is true for n equals 1. Well, of course, it doesn't have to be 1 all the time. We just have to show that it works for the first time. In this case, the n was the positive integer, so the base case was n equals 1. And then we show that we assume that for n equals k, the proposition is true. And then we use that mathematical expression that 4 to the power of k plus 2 is equal to 3m, where m is an integer. And we actively use that statement in the process of proving the n equals k plus 1 case. So you plugged in the values and you got the expression 3 times 4m minus 2, which is a proof that 4 to the power of k plus 1 plus 2 is divisible by 3. So we did all the 3 steps, so I think we can conclude. In conclusion, 4 to the power of n plus 2 is divisible by 3 for n for positive integer values of n. When you do the mathematical induction process, because we're trying to prove a proposition, so the mathematical correctness doesn't matter too much. What's more important is the presentation of your work. And when you're presenting the mathematical induction, we need to make sure that we show the base case. And we need to explicitly show that we're testing the n equals 1 case. So maybe you can write it exactly like how I did here. Base case, show that the proposition is true for n equals 1. Or you can say for a p of n equals 1, whatever you want. But you want to show that you're testing for n equals 1. And then you also want to write down, especially the word, you're assuming that for n equals k, that proposition is true. You want to write that statement explicitly as well. And then finally, you also want to explicitly write that now, using the assumption, we're showing the n equals k plus 1 case. And then finally, we can also say that it's proven by mathematical induction. Maybe you can also finish with a little square to note the end of this sentence in the proof. All right, let's try one more example. Prove that the sum of I squared from I equals 1 to n is equal to n times n plus 1 times 2n plus 1 divided by 6. All right, so this problem looks very, very complicated, doesn't it? Well, even the power of the proof by mathematical induction is that no matter how difficult the problem looks, if you follow those cases, the base case, and then n equals k assumption, and then n equals k plus 1 proof, it can be solved quite easily. So first of all, let's also start with the base case. Prove that the proposition is true for n equals 1. So let's replace this entire expression with n equals 1. So that's going to be sum of I squared from I equals 1 to 1 is equal to 1 times 1 plus 1 times 2 times 1 plus 1 divided by 6. So what is the sum of I squared from 1 to 1? Well, we just have 1k, so that's 1 squared. And then the expression here will be 1 times 2 plus 1 is 3. So I think we get 1 equals to 1. So yes, we have proven that the proposition is indeed true for n equals 1. We know that the base case is true. In other words, we know that we have knocked off the first domino in the domino set. Now let's move on to the next case. We assume that the proposition is true for n equals k. Once again, what I mean by that is we're going to write down the expression that for the sum of I squared from I equals 1 to k is equal to k times k plus 1 times 2k plus 1 divided by 6. So I know this is true. I'm going to assume that this expression is true. Now, not many people like this summation notation, so maybe you can try to rewrite this expression as 1 plus 1 squared plus 2 squared plus 3 squared plus dot 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 all the way to k squared is equal to k times 2 k plus 1 times 2k plus 1 divided by 6. Maybe the second equation will be a bit more useful to use when I'm trying to prove the next case, which is the goal is to prove that proposition is true for n equals k plus 1. So now let's write the proposition first, and then we'll try to prove that. So we want to show that the sum of I squared from I equals 1 to k plus 1 now is equal to k plus 1 here, and then k plus 1 times 2 times k plus 1 plus 1 divided by 6. All right, so, well, my left-hand side, I know I can rewrite this expression as 1 squared plus 2 squared plus 3 squared plus dot 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 plus k squared plus k plus 1 squared, right? And I think I can also simplify the right-hand side slightly. I can say it's going to be k plus 1 times k plus 2 times, if I expand this, 2k plus 2 plus 1, so 2k plus 3 divided by 6. Now, so once again, reminder that when you're doing the last step, when you're trying to prove the proposition is true for n equals k plus 1, we always want to make sure that we're using the assumption that we just made from the previous step. So it means that, hey, 1 plus 2, 1 squared plus 2 squared plus 3 squared dot 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 plus k squared is indeed equal to that expression. So I think I can replace the most of my left-hand side with that, cannot I? So that means that I can rewrite this as k times k plus 1 times 2k plus 1 over 6 plus k plus 1 squared. So now I think if I can show that my left-hand side and right-hand side are equal to each other, I think we'll prove that the proposition is true for n equals k plus 1 case. So I think we should try to expand some stuff, right? Um, I think my life would be better if I can factor out the k plus 1 from both sides first. So, well, actually, I'll try to match the denominators of each fraction first. So I think I can say k times k plus 1 times 2k plus 1 over 6 plus 6k plus 1 squared over 6. And then I'll factor out k plus 1 from both terms, which is going to become k times 2k plus 1 as the first term plus 6 times k plus 1 as the second term. Now let's expand the second factor. 2k squared plus k plus 6k plus 6. So that becomes k plus 1 times 2k squared plus 7k plus 6 over 6. Now, I'm not going to expand this one step further because I think I can go easier the other way around. What I'll do is I'm going to leave the k plus 1 outside in the first place, but then I'm going to expand the k plus 2 and the 2k plus 3, these two terms. So if I do that, it'll become 2k squared plus 4k plus 3k, so that's going to be plus 7k, plus 2 times plus 3, so that's 6. And then we have shown that the left-hand side and the right-hand side have the same expression, so this is proven by deduction. Remember, the proof by deduction is the process of showing the left-hand side and right-hand side are equal to each other. So what did we do here? We proved that, therefore, the proposition is true for n equals k plus 1. So once again, we did all the 3 steps. Remember the 3 steps for the proof by mathematical induction. The base case, the assumption for n equals k, and the proof for n equals k plus 1. And because we've done all 3 parts, we can definitely say that the proposition is true for all n, that is a positive integer, or all positive integers of n. And it's how is it done? It's proven by mathematical induction. Alright, so once again, before I finish this video, make sure that you're using those 3 steps and you're explicitly showing those 3 steps when you're using the proof by mathematical induction method to solve problems here.